Okay, so let's just think a little bit about the state that we can have of our spin magnet. So the first thing that we might ask is, well, what is the lowest energy state? And that'll be the state that minimizes the Hamiltonian. And in fact, there are two such states. So the one state has all of the spins pointing up. So everything points up. This is the first state. But there's a second state of lowest energy, which has all of the spins pointing down. And of course, these two states are different. You can certainly distinguish them by looking, for example, at the values of the spin. This will keep going. We imagine we've got very many spins. So each of these states has a degeneracy, like degeneracy equal to 1, both states. So if we think about these are lowest energy states, but they also have a very, very low entropy. So now how can we get a state of a slightly higher energy? Well, we could flip one spin. So if we flip one spin, that's definitely going to increase the energy. Why? Well, when we're summing over this Hamiltonian, so let's just imagine that we flip the spin somewhere. So for this one spin that's pointing down, when we sum its contribution from its neighbors, we're now going to get a positive contribution to the Hamiltonian. So we'll be adding some energy because we flipped one spin. If we want to flip one spin, how many states are there? Well, you could pick which spin you want to flip. So there are n states because you can flip any one of n spins. Okay, so I'm going to always use n will be equal to the total number of spins. Then we could get an even slightly higher energy state. So by repeating this trick, so we increase the energy by flipping one spin. Well, if we flip two spins, we'll add even more to the energy. Okay. And now how many ways are there to flip two spins? Well, go ahead, you check, but I'm telling you, it goes something like n squared over 2 states when n is very, very large. And then we can keep going. If we flip 3 spins, then we'll have something like n to the 3 over 3 factorial states. Now, so what you see is the energy is growing because every time we flip a spin, we add some energy to the state. But the other thing that's happened, we had one state, then we had n states, then n squared over 2, then n cubed over 6. So this means that the entropy is also growing. Entropy also growing. Okay, so this is how the state starts to behave. Now, one more thing that we should discuss. So let's take our Hamiltonian. So I will want it below. So let me just copy it. Okay, now what do I want to do? Is here's a Hamilton, consider our ground state. There's two possible ground states. So how do we choose which ground state we land up in? Well, the way to do that, we're going to introduce one more dial that we can choose. We're going to introduce little h. Oh, sorry, little h. This is an external field. And I'm going to introduce it in such a way that the spins like to align with it. So I will add a term which is minus h, and this will just couple to the total magnetization of the system, the sum of R of a sum. H is an external field. I will imagine that I can take the values plus or minus b. Now, one more thing we have to introduce, and then we can start doing some physics. We need to introduce what is known as an order parameter. What is an order parameter? This is a quantity that will distinguish phases. We'll distinguish between possible phases. So let me tell you what the order parameter is here for us, so that you get a good idea of what it is. The order parameter M is just given by summing over all of the spins, the value of the spin. So if you look at these low energy states, with this low energy state at the top here, if we worked out what was the magnetization would actually be equal to N, because we're just summing one for all N spins. Now, in general, N is going to be enormous, Avogadro's number or something like that. So it makes sense to normalize our magnetization by 1 over N. And then the value of the magnetization in this state becomes completely independent of the number of spins, and it's just equal to 1. For this state over here, N is equal to -1. Now, for this state, M is positive. But, well, for all of these states, M would be positive, but just less than 1. So let's write M is less than or approximately equal to 1. And as we start to flip more and more spins, so the magnetization gets smaller and smaller. If we went all the way up to a very large entropy state, well, that would be something with half of the spins pointing up and half of the spins pointing down, and that would just have a magnetization of 0. So now let's draw a plot summarizing some of this physics. So here on this axis, I'm going to imagine on this axis, I've got my external field, okay? So this axis is for my external field. Along this axis over here, I'm going to have temperature. Now let's start off over here. So very small external field, very low temperature. Then we know the magnetization is 0. Actually, at this dot over here, right next to the origin, well, there I know that the magnetization will actually be equal to 1. As I move away from the origin, the magnetization starts to drop off. It's no longer 1, but it's still positive everywhere along here. Okay? What about if I'm just below the axis? Well, at this point over here, M will be less than 0. So how do I know which low energy state I have selected? Well, you know, at this point over here, I've got an external magnetic field. It's definitely going to pick the state with all of the spins pointing up. And then I can slowly switch that field over. And if I do that, I'm left with all of the spins pointing up. Conversely, you know, I could have started over here with a negative external magnetic field. That would have caused all of the spins to point down. And then I slowly switch off that field, and I'm left in the state where all of the spins point down. Good. So these are all positive. But as you move along this line, so the magnetization starts to drop off, and you get to some point where the magnetization is actually 0. So let me just draw a jagged line along here, just to remind you that the magnetization, the order parameter, is discontinuous across this jagged line. So for example, if you're just this side of the jagged line, the value of the magnetization above the line is very small, but it's positive. And just below the line, it's very small, but it's negative. Over here, if you go from the top plane to the bottom plane, above the line, the magnetization is positive just because the B field is causing spins to point up. Then you slowly switch off the B field, switch it off, switch it off, switch it off. By the time you get to 0 B field, the magnetization is actually 0. Then as you go down, the magnetization now becomes negative. So in the presence of no external field, we've got so many spins, we've got the high entropy state, so roughly half the spins point up, half the spins point down, and there's no net magnetization. So this point over here, this is a fascinating point, because just to the right of this point, entropy wins the competition, and just to the left of that point, energy wins the competition. So somewhere over here, okay, where we are talking about this discontinuous value of m, so in this region over here, we would say that we have the first order phase transition, or we've got a discontinuous phase transition. But at this point over here, where we got this point, here we would say we have a continuous phase transition. It's also called a critical point. It's also called a critical point. And it is this point that is described by CFT. So we're going to argue why CFT describes this point. The CFT doesn't describe the phase transition everywhere. It's just at this temperature where you're transitioning from a state with no magnetization to a state with magnetization. So it's just at this point where energy and entropy are exactly balanced. Okay, we'll continue in a moment.